Hi and welcome everyone. My name is Jakub. I work as a technical pre-sales expert at Capturing Reality, and I would like to talk about merging terrestrial laser scanning with photogrammetry in RealityCapture. In this tutorial, I am going to reconstruct the exterior of a small Gothic church. I will be using 4 datasets. Each of these datasets was acquired with a different camera and one was acquired with a terrestrial laser scanner. What is interesting is that each of these datasets was acquired in a different day, sometimes even months apart, but I was still able to align them all together in RealityCapture. First, I will introduce you the datasets. Then we will align the datasets separately and export them as components to demonstrate you the component workflow. Once all the components are prepared, we'll bring them all together and continue with the automatic alignment. One of the datasets was captured in a way that the automatic alignment will not work because there is no overlap between the images and the rest of the datasets. And to merge them, I will show you how to use control points. After we finish the alignment, we will reconstruct the mesh, filter out the unwanted geometry, and finally texture the mesh. Let's start by introducing the datasets. Like I said before, we have 4 datasets. The first one contains 483 images and is from a drone that was controlled manually around the church. The second dataset was acquired from the ground with a mirrorless camera. This dataset contains 76 images, and these images were used to help the automatic alignment between the manual drone flight and the laser scans. The last image dataset contains 76 images, and it was an automatic drone flight in a single grid pattern in 50 meters altitude above ground level to capture the wider area of the church. The laser scanning dataset is containing 10 scan stations. These scans were previously registered, or in other words aligned, in a laser scanning software, and later they were exported as ordered PTX point clouds. At this moment, RealityCapture supports ordered E57 and PTX point clouds. After launching RealityCapture, we will import our first images. In this first project, we will align the images from the ground with the images from the manual drone flight. I will import the images using the inputs icon in the workflow tab. They can also be imported by drag and dropping the images into the user interface. I will select all of the images by pressing Ctrl A and click on Open. Next, I will import the images from the manual drone flight the same way I did with the images from the ground. Now with all 559 images in the project, we can start the alignment. The alignment finished after 8 minutes and 20 seconds. I'm using a laptop with 6-core i7 CPU with 2.2 GHz, 16 GB of RAM and NVIDIA GTX 1060 running on Windows 10 OS. When I click on the created component in the 1Ds view, I can check the alignment report containing more information, the alignment time for example. Now I am ready to export the registration. I will go to the alignment tab and click on export registration. I just need to select the proper folder where I want to export my component. After it is done, I can create a new project. And this time I will import the laser scans. I will use the Import Laser Scans tool in the Workflow tab. I will select all the PTX point clouds and click on Open. RealityCapture will display the Import Laser Scans dialog where we have a few options. Because the laser scans were already aligned in a laser scanning software, I will choose the registration as exact because I do not want RealityCapture to change the positions of the scan stations. I have 2 other options if I want to optimize the registration or if the scans are not aligned at all. The laser scans are not georeferenced and they were scanned with color. It is possible to align images with laser scans without color in RealityCapture, but we always recommend our customers to scan with color. The only thing that I changed was the folder for the converted laser scans, because RealityCapture converts the scans to LSP files, and the next time you would like to use them, you can import them just like images and skip the whole import laser scan tool. The import finished after 1 minute. Right now, we do not see anything in the 3D view. To view the point cloud, we have to click on Align. Now we can see the point cloud, but you may notice that it is not as dense like you've seen it in the laser scanning software. You don't have to worry about it at all because all the points are stored in the memory and will be used during reconstruction. When I click on the component, we can see that the alignment time is 0 because the registration was imported as exact. This time I will save the project because I will use it later to import the other components and align them together. After it is saved, I will create a new project for the drone automatic flight. Instead of inputs icon, I will use the folder icon to import a whole folder that is containing the images. 76 images were imported and I can just click on align. This time we had fewer images, so the alignment finished quickly in just 1 minute. We can see the sparse point cloud with the camera positions. Now I will repeat the whole process like with the first dataset and export the registration. Again, the export tool is located in the alignment tab. Now I will go back to the saved project with the laser scans so we can proceed with the automatic alignment without control points. To import a component, go to the alignment tab and use the import component tool and search for our first component that is containing the images from the ground and from the manual drone flight. After the import, we can see a new component in the 1Ds view, and next to it we can see a star icon, and this star is symbolizing that this component was imported. Since I already processed these datasets before recording this video, I know that I need to change the detector sensitivity from medium to high for the automatic alignment to work on the first try. Let's do that right now in the alignment settings. Also, I'm going to change the merge components only from no to yes for this case. When set to yes, the application will not align new images, it will only join components. But do not forget to change this option when you start a new project, otherwise RealityCapture will not align your images in the new project. After changing these settings, I can just click on align and wait for the alignment to finish. This time the alignment finished in 1 minute. The lines that you can see in the 3D view are residuals, and they are showing the difference between the original position of the cameras and the adjusted position after merging with the laser scans. It is not a problem at all, and I can disable them from the Scene Context tab. After the alignment, RealityCapture created a new component that is containing all the images in the project. For the sake of keeping things organized, I can rename the component to Merge without control points. Now let's continue with the alignment with control points. This time I will import the component that is containing images from the automatic drone flight. The component was successfully imported to the project, and I can delete the older components because I no longer need them. This time I will merge the already merged component without control points with the automatic drone flight component. I will change the application layout to 1+2 for more comfortable placement of control points. I want to see the 3D view containing the sparse point cloud. It will be used for placing the control points, and I also want to see the 2D view for visualizing the control point suggestions in the images. To activate the placement of control points, I need to go to the Alignment tab and click on the Control Point tool. While the text is highlighted, the tool is active, and now when I hover the mouse cursor over the sparse point cloud in the 3D view, I can see image suggestions in the 2D view. And to place the control point, just click with the left mouse button. While I am placing the control points in the 3D view, I don't have to be that accurate because I will later refine the control point position in the image suggestions. Because there are no targets or markers in the scene, and because the datasets were acquired in different days, the only similar features in the images were the tombstones or the church itself. So I decided that I will use the tombstones for placing the control points. I placed 3 control points in the first component, and 3 points is the minimum for the alignment. We recommend you to use more, and they should also be evenly distributed in the overlapping areas of your components when it is possible, of course. In the 1Ds view, we can already see some image suggestions under the control point's name. So I finished with the first component, and now I have to place the same control points in the second component, and I need to place them to the same spot. To place an existing control point, it needs to be highlighted in the 1Ds view. Otherwise, after clicking, I would place a new control point. On the last control point with the number 2, I wasn't entirely sure which corner of the tombstone I picked, so just in case I went back to check the correct position. After the control points are placed in both components, I can disable the control points tool and start with refining the position of the points in the image suggestions. I can change the application layout back to 1+1 and change the large window from 3D to 2D. I will select the first suggestion under control point number 0, click on the control point in the 2D view with the left mouse button, place it to the correct spot, and while I'm still holding the left mouse button, I will press the Enter key, and this way the application will confirm the point's position and will automatically switch to the next suggestion. This way you can place a lot of control points in a relatively short time. I will repeat the process for all of the suggestions, and for the second and the third control point I speed up the video because the process is exactly the same. Once we are finished, we can check the point's position in the 3D view in both components. Before the alignment, we can save the project, and after it's saved, we can just click on Align Images. This time the alignment finished in 2 minutes and 38 seconds. We have a new component that is containing 694 images out of 694 images. I can change the scale of the cameras to make them more visible in the Scene Context tab. After the alignment is finished, I can continue with the reconstruction. First, I will adjust the size of the reconstruction region from the top view. I'll be using the colored circles to manipulate each side of the region. Next, I will switch to one of the side views and adjust the top and the bottom of the reconstruction region so we are not cropping out some parts that we would like to reconstruct. When we are ready, I can go to the Reconstruction tab and start the reconstruction of the mesh by clicking on Normal Detail. On Normal Detail, RealityCapture will downscale the original images by the factor of 2 on the default settings. The reconstruction finished in approximately 1 hour, and if the scene is containing a lot of polygons, you can get this warning sign that you do not have enough video memory to display all the polygons. My graphics card with 6 GB of RAM can display up to 40 million polygons, but my mesh has more polygons, and that is why I can only view the dense point cloud in the 3D view. If you do not want to see this warning sign again, just check Do Not Show Again and click on Close. RealityCapture reconstruction algorithm creates watertight meshes, and that means that we also have large polygons on the bottom side of the mesh. Also, we can see that we have some floating tree branches next to the church. So now I will show you how to get rid of these bottom polygons and also how to get rid of the floating unwanted tree branches. To delete the bottom polygons, go to the Reconstruction tab, pick the Advanced Selection tool, and use the Select Marginal Triangles tool in the 1Ds view. RealityCapture will select the bottom polygons, and to delete them I will click on Filter Selection. RealityCapture will create a new mesh, but this time without the selected polygons. We still have the floating tree branches, and there are multiple ways how to select them, but I can use the lasso tool to select a small part of the church, expand the selection, invert the selection to select the tree branches, and possibly some other floating geometry that we didn't notice before. To delete the unwanted polygons, I will click on Filter Selection again. Just as a side note, for selecting the largest connected mesh part, I could have used the Select the Largest Connected component in the Advanced Selection tool. After our mesh is cleaned, we can start texturing it. To check out the settings, let's go to the Texturing settings in the Reconstruction tab. By default, RealityCapture will create one texture with maximal texture resolution of 8K. If you want to get the best possible quality of your texture, you need to change the texturing style to Fixed Texel Size and change the Fixed Texel Size to Optimal. On these settings, RealityCapture will create as many textures as needed to get the 100% texture quality. In the beginning, I mentioned that we have our laser scans with color, but because the onboard cameras in the laser scans have lower quality, I will disable them for the texturing process because I do not want them to lower the quality of the final texture. I can select them in the 1Ds view, and in the 1Ds view I can also disable them for texturing. After disabling the laser scans, I can go to the Reconstruction tab and click on Texture. The texturing finished in 30 minutes, and now we are looking at the final textured mesh. I already simplified it to 1 million polygons so we could see the textured mesh in the sweep mode instead of vertices mode that displays the dense point cloud only. For comparison, I also prepared the exact same mesh but textured using the laser scans only, and right away you can see the huge difference in the texture quality. And that's it. We reached the end of this tutorial. To recap, we had 3 datasets of images, 1 from the ground, 2 from the air, and 10 laser scans. I showed you the component workflow, alignment with control points, and alignment without control points when there is not enough overlap between the images. We reconstructed the mesh, deleted unwanted polygons, and finally textured the mesh. Thank you very much for your attention and stay tuned for future tutorials. Bye!